So good morning to one and all. Today we are learn here a partition into groups. So before that we will see here the definition of a partition into groups. So a partition of a set. So the word partition is I think it is a familiar with you in your day-to-day life, because partition means we have to take a part, and here also we have to take a parts of that group. Yes. So a partition of a set into a groups involves dividing a set of elements into non-overlapping subsets where each element belongs to exactly one subset. It means that if you take a group contains 5 elements, suppose A, B, C, D and E. Yes. So each and every element is also form a subset. So those subsets are called as a groups of that partition. Yes. So depending on the context, the order of these groups or the order of an element within each group may or may not be matter. So when a partition a set into groups, the focus is now how the elements of a set can be divided into distinct subsets. So the primary concern is the grouping structure rather than the order of the elements of the or the groups unless specified otherwise. Yes. So what are the factors which are affecting the number of partitions? So there are uh, uh, three factors which are affecting of number of partitions. So the first one is size of the set, second one is number of groups, and the third one is distinguishability. Yes. So size of the set, it means that the number of elements in the set is partitioned, or you can partitize the set is what is the size of that set, that we have to check. The second is number of groups, means the number of non-overlapping groups or subsets into which the set is to be divided. Yes. And distinguishability means whether the group are distinguishable. It means that each group is unique and identifiable. Yes, or identifiable. Or indistinguishable means where the groups are identical and cannot be distinguished from one another. Yes. So these are the factors which are affecting to find out or to form a partition of a group. Yes. So next, how we can find out here the number of ways in which that elements can be divided into the two groups. So for let us see here the number of ways in which m plus n elements can be divided into two groups containing m and n elements respectively, and it is given by m plus n factorial divided by m factorial into n factorial. So see, this is the statement of the theorem that we have to prove here. The result, if there are m and n, m plus n elements, and we have to divide these elements into two groups containing m and n elements, then you can find out the number of ways how we can divide these two groups, these elements into two groups, and it is given by here m plus n factorial divided by m factorial into n factorial. So how to prove this result? So to prove this result, already here the two groups we have to show, and here the m and n elements are given. So to prove this one, consider a set of m plus n distinct elements, and we want to divide this set into two groups. So one containing m elements and other containing n elements. Yes. So first we have to choose m elements from the elements m plus n. So both these two elements are together, and that we have to take a partition of these in m and n, both two separate sets. Yes. So the number of ways to do this is given by the formula of a combination, and it is m plus n cm is equals to, just you can apply the definition of a combination. So m plus n factorial divided by m factorial in another bracket m plus n minus m factorial, because here NCR, you know the formula for combination is NCR is n factorial upon r factorial into n minus r factorial. And just you can compute it, we get m plus n factorial divided by m factorial into n factorial. So this is your required result, yes, and the remaining, and so this is the result for choosing m elements from the m plus n elements. So the remaining n elements automatically form the second group. Once you can segregate or particize or separate m elements, automatically you can get the second group and it contains n elements, and hence the order within each group does not matter. This count represents the number of ways to partition the m plus n elements, yes, so into two groups of the sizes m and n respectively. Hence the number of ways to do this is m plus n factorial divided by m factorial into n factorial. And so this is the your required result for the theorem, yes. So the proof of this theorem is complete. Now let us see some remark is also on this theorem, and these are the special cases. If m and n is same, what happens? So here when m and n is same, then the formula simplifies to 2n factorial upon n factorial raised to square, yes, and this expression represents the number of ways to split 2n elements into two equal groups of size n, yes, and hence the group are indistinguishable, each of size n, and then the number of different partition is given by here 2n factorial upon 2 factorial into n factorial whole square. So are you understand how the difference between if m is equals to n and just you can split the number of ways to the split to 2n elements into two equal groups of size n, then you can write divided by 2 factorial. So are you understand difference between the 2n factorial upon n factorial whole square, this if m and n is equals, yes, just you have to divide by 2 factorial. So now we will see the example on this partition of a group. So the first example is, you can consider the 4 elements. So this one. So to illustrate the concept, consider the set contains the 4 elements A, B, C and D. Yes. So let's partition S into 2 groups of 2 elements each. So are you understand? Here the theme of this example is 4 elements are given, and we have to take the partition of this set S into 2 groups of 2 elements, yes, and the condition is here, if the groups are distinguishable, means that the labeled groups are there, then what are the possible partitions here, and here I have shown these partitions. What are the possible partitions are here? We have to select the 2 elements, yes, from the set S. So A, B, C, D. So this is the possibility. Another possibility is AC, BD, then AD, BC. Yes. So only these are the possibilities to form a partition of the group or of the set. Yes. Now, if the groups are indistinguishable, means unlabeled, then all pairs of partitions where the groups are swapped are considered the same. Yes. Hence the possible partitions are ABCD, ACBD and ADBC. So are you understand how we can distinguishable and indistinguishable groups we have formed from the set S? It contains the 4 elements and we have to take the partition with at least 2 elements are there. Yes. So now we will move to the second example, and this is the extension of the 3 groups. It means that the number of ways in which m plus n plus p elements can be divided into 3 groups containing m, n and p elements, yes, respectively. So it is given by m plus n plus p factorial divided by m factorial into n factorial into p factorial. So I think you have understand very well. Just you can extend the concept of number of ways in which m plus n elements can be divided into two groups. Here we have to now find out the number of ways in which the m plus n plus p elements can be divided into three groups. Yes, so this is the difference. And now you can extend, but before the extension you can solve or you can prove this result also. And proof is straightforward. Previous one we have already solved the proof for two elements m and n. Yes, so here also to prove this we have to consider a set of m plus n plus p distinct elements, and we want to divide this set into three groups containing the elements m, n and p respectively. So first you can choose the m elements for the first group, and the number of ways to do this is given by the definition of a combination. It is m plus n plus p c m. Yes, just you can choose the first element, it is a m, and that's why we can write it as a cm and apply this definition, which is equals to m plus n plus p factorial divided by m factorial in another bracket n plus p factorial. Yes, so in this way you can choose now n plus p group. Already you have choose m group, m elements. After that you can take the partition of remaining elements, and that is n plus p. Yes, so after selecting the first group m elements, then you can leave to the n plus p elements, and now choose n elements from second group. So the number of ways to do this is already we have proved this result for two elements m and n, and so this result is also the same. Just the m is replaced by p here. So n plus p cn is equals to n plus p factorial divided by n factorial into p factorial. Yes. Now look at here the remark on above theorem. So the special case for this one is if m, n and p are same, then the formula is simplifies to 3n factorial divided by n factorial whole cube. So this expression represents the number of ways to split 3n elements into three equal groups of size n. Yes. However, if the groups are indistinguishable, each of size n, then what happens? Just you can divide here by 3 factorial. Already we have proved this one is also for two elements. So the partition of this one of size n is given by here 3n factorial divided by 3 factorial into n factorial whole cube. So I think are you understand the concept by extending for a 3 partition or 3 groups of partition. Yes. Now let us see here one example of partitioning a set of 6 elements. Yes. So to illustrate this, we can consider the set S contains the 6 elements A, B, C, D, E and F, and we have to partition this set S into the 3 groups of 2 elements each. So you know, if the groups are distinguishable, then the possible partitions are A, B, C, D, E, F, A, C, B, D, E, F, A, E, B, C and C, F. Yes, and so on. If the groups are indistinguishable, then all permutations of these groups where the order is swapped are considered the same. Hence, if we initially have A, B, C, D, E, F, just you can set any two of the groups would result, yes, would result the same. Yes, partition, and hence the total number of distinct partitions are given here. Now we will conclude here this lecture, and thus the number of ways to partition the set S into 3 groups of 2 elements each where the groups are distinguishable is 6 factorial divided by 2 factorial whole cube, and it is 90. So if the groups are indistinguishable, then the number of partition would be reduced by 3 factorial. Just you can divide it by 3 factorial. We get 15 distinct partitions. So I think all of you are clear the concept of partition of a group. So in this lecture we will discuss the definition of a partition. Then we will discuss the theorem, which is a result of if m and n, m plus n are the elements, then we have to take the two groups of these elements m and n, and it is given by m plus n factorial divided by m factorial into n factorial. After that, we have discussed the cases of distinguishable and indistinguishable groups. Yes, and also we have studied the remarks for if m and n are same, then what happens, and also we can extend the same result for three groups. Yes, so we will stop here.